Okay, so now we're recording. So we ended last class period talking about the signs of the zodiac. The zodiac basically means the zoo. And the signs of the zodiac are the constellations that fall. There are 13 constellations here that fall within, I think it's plus or minus 18 degrees of the ecliptic. Now, we've already talked about the ecliptic. It's once again defined here. The ecliptic is the path, if you want to be technical, it's the path pointing from the sun out to the earth and then out to the celestial sphere as the earth orbits the sun. That's the correct definition. The one we usually say is it's the path the sun appears to take going around the earth. Notice the word appears because the sun isn't going around the earth. But that's the way it appears to us. And remember, I talked about, in theory, your sign of the zodiac is where the sun was when you were born. But that's only in theory because of the shift in calendar, which we should get to today. So the earth going around the sun results in what we call the annual motion. We define the year as the time it takes for the earth to do a complete orbit around the sun. Now, one of the first and foremost things that's interesting about the Earth's orbit around the sun is that the Earth is tilted 23.5 degrees. Well, you can see there it's technically 23.44 degrees, which doesn't round to 23.5. It rounds to 23.4. But the textbook says 23.5 and has pictures say 23.5, so I'm going with that. For our level, it doesn't matter. We're tilted about 23.5 degrees from the axis that we are orbiting around the sun. So that means if this stylus was the Earth, the North Pole is this tip here. At one time of the year, we're like this, and the North Pole is pointing roughly away from the sun, tipped back. But you go around, of course, I'm going in the wrong direction for what we usually do. Here, the North Pole and South Pole are equidistant from the sun. Come over here, now the North Pole is roughly pointing toward the sun, and South Pole away. Well, if you're facing more of the sun, you'll get more sunlight, right? That's kind of obvious. You get more sunlight, what happens to temperatures? They go up. And so this is what causes our seasons. Our seasons are caused because we're tilted. And so the time of year when it's like this, we're in the northern hemisphere, so we're up here. If we're tilted like this, now we're up like that, so the south is closer and the north is farther away, are we going to be getting more or less sunlight if we're tilted away from it? Less. So what season would you expect that to be? Winter. Now, winter actually starts at the moment that we are getting the least sunlight. And it continues on after that until we get to the equinox, which is when we're over here. So winter starts at that moment of getting the least sunlight. We're going to have a clicker question that actually relates to that coming up here soon. It has dates on here. December is when we are tilted, so the northern hemisphere is mostly pointing away. Notice the sun lights up half of the earth. It's always going to light up half of the earth. Actually, there's slightly more because of atmosphere bending light, but once again, for our purposes, we can say the sun lights up half of the earth. But in December, that half is lit up. The South Pole, no matter how you rotate, the South Pole is going to be lit up. So the sun won't set on the South Pole in December. And in fact, there is a band here where the sun won't set. Now, how much is the Earth tilted? 23.5 degrees. So if the Earth is tilted 23.5 degrees, then it turns out that this band here, where the sun will never set, is 23.5 degrees away from the pole. And so we call that region down there where the sun will never set in December the Antarctic. And this pin is not going to work if I go on to... I tried to change color. You can see it didn't work. Why is it 23.5 degrees from the pole? Simply because the pole is shifted 23.5 degrees out, and so the part that's at the bottom is 23.5 degrees from the pole. And as it rotates around, everything that's closer to the pole than that will always see the sunlight. Now, at the other side, we're going to have everything that is in this region doesn't see the sun at all. And that there is the Arctic. And where do you suppose that is as far as the angle from the pole? I know you know. Yeah, it's going to be 23.5 degrees because it's the same geometry, really. So our Arctic and Antarctic are both 23.5 degrees from the pole. Now, let's do really hard math. The pole is how many degrees from the equator? "90 degrees. So if it's 23.5 degrees from the pole, how far is it from the equator? So it's 66.5 degrees from the equator. Why did I do it from the equator? Because we measure both latitude and declination from the equator. So the Arctic Circle is going to be 66.5 degrees north latitude. The Antarctic Circle, 66.5 degrees south latitude. That's how we define the Arctic Circle and the Antarctic Circles, by where on the solstice, when we have that maximum pointing away or pointing towards where the sun shines and doesn't shine. Now, the equinox, half the earth is lit up. So everywhere on earth is going to be half day and half night, except if you're right at the pole. If you're right at the pole, it's just twilight the entire time still at the equinox. And then we go to, now we're in the northern hemisphere. We're right here. What season is it going to be? Summer, because we're getting a lot more sunlight. Notice that sunlight is hitting at a more direct angle on the surface. Over here, what sunlight we did get was hitting at a very glancing angle, which means the actual amount of light per square meter is smaller in the wintertime, even though we get sunlight. A second factor is we don't go through a full half rotation with sunlight in the winter. In the summer, we go through more than a half rotation with sunlight because of that tilt. So summer days are longer than 12 hours of daytime, shorter than 12 hours of nighttime. Winter days are just the opposite. So summer, more direct sunlight, longer periods of sunlight. Well, yeah, you're going to bake more. Daylight savings time is, yes. We usually credit Ben Franklin for coming up with daylight savings time, but I've read, no, that's actually not true. But the idea of daylight savings time is to save energy by having people up and about when the sun is up, not waking up when it's still dark and having to turn on lights. And so that's the idea of saving energy, not having to turn on lights. And these days, while one side of it says we need to be friendly to the environment, the other side of it says, I don't like shifting the clocks. Everybody wants to get rid of it. And some people have suggested that maybe it's not saving that much energy. I think it is, but I haven't crunched any numbers. Do you have a question?
No.
Okay. Well, not really. Kind of? Okay. I was thinking of one, but I wasn't going to verbalize it. All right. So when we talk about these positions, we have positions and they occur at specific times. So the summer solstice, that's going to be the time when we are tilted. So the northern hemisphere is pointing as much as it can toward the sun. And that date comes about June 22. It's a specific time each year when we, if you're like, well, got tilted the other way from what I've been doing, you come like this, and when you get to just this position, there you're at the solstice. You keep going, and you move away again. So it's a specific time. You can also view it as actually a specific place on the celestial sphere, because we will always see the sun at a very specific place at the solstice. And that's why the Stonehenge worked the way it did, because they knew where the sun would be at that specific day. So it's a time, it's also a position in the sky. Winter solstice is just the opposite. And of course, we have the two equinoxes, the vernal and the autumn. I get autumn and spring and fall. There's only two things out of those three. And then vernal. It always messes me up. I think it's autumnal and vernal. But I hate getting words all confused. One thing to note here, actually, I should point out, I think this is in your homework actually. The equinoxes occur at the locations on the celestial sphere where the ecliptic crosses the celestial equator. So you can look at a celestial sphere model, find where those two meet, you say, there's the vernal equinox, there's the autumnal equinox, where they cross. And so vernal is around March 22. Hence, we have spring break around that time because that's when spring starts. And autumnal is around September 22, and that's when fall starts. It varies by a day or two because, we have our whole leap year system to try to account for the fact that the year is not exactly 365.25 days. Okay, here a common myth. I didn't ask you guys this question, but a lot of people just tend to believe that summer is caused when the earth is closest to the sun and winter when it's farthest from the sun. Now, it's very true. When you're closer to the sun, you're going to get more radiation from the sun. Does anyone know roughly? Does it say it there? It kind of does. When the earth is closest to the sun? January 4-ish. It changes over time, but right about now it's January 4. When I started teaching astronomy, January 5. It slowly moves through the calendar. So we're closest, we call that the perihelion on January 4. Does that make it summer here? No. What if you were in Australia? Yes. The seasons are opposite in the northern hemisphere and the southern hemisphere because the seasons are based on the tilt, and when the northern hemisphere is tilted away from the sun, surprise, the southern hemisphere is tilted toward it. So we have opposite seasons. So the southern hemisphere summers are a little bit warmer than average because they're both closest to the sun. Well, they're closest to the sun when they're receiving the most radiation. So they're having more extreme seasons. Likewise, they're farthest away from the sun during the winter, so their winters are a little bit colder than average. In the northern hemisphere, we're a little more moderate on both sides. A little bit warmer winters, a little bit cooler summers. Most of the landmass of the Earth is in the northern hemisphere, and so we build up ice on the northern hemisphere, and it makes a bigger difference for the Earth's climate, what's going on in the northern hemisphere because of that. And so right now, with the milder changes in the weather, we should be undergoing a warming trend because of the not building up so much ice mass, which has a lower albedo, which is just a fancy word for reflectivity. The less ice we have, the less energy we reflect, and thus the more energy we absorb from the sun. Anyway, so that's part of what drives our climates. We'll talk later on about the Milankovitch hypothesis about all of the things in astronomy that drive the climate on Earth. Whoops, that was the wrong thing to do. Okay, I've already talked about everything on this slide, so let's have our first clicker question. Okay, answer this time. All four of you who have registered. I look at Amelia, Daniel, Aldwin, and Gabby.
What? I don't got a license. I can't answer it.
Yeah.
I might have been registered, but it's not going to show up. I promise you that.
Remember, on Monday, it will start counting.
Okay, got you.
Thank you, Amelia. Okay, so we have an answer. And I was thinking it was you last time rather than her when two lectures ago. Oh, were you?
What's the channel?
33. So you'll be in on the next one? Rocking it. Okay, so do you go as Amelia or Amy or? Amelia, okay. So winter solstice occurs on December 21. What is the coldest month in the Northern Hemisphere? What would the rest of you have answered? I know what she answered. By the way, this is also a homework question. Actually, the homework question is about hottest rather than coldest, but same idea. January? Matt?
I've always heard that the coldest month is January.
January? Okay, that's what she answered too. Everybody's answering January. It's between January and February. Depends on where you are and whatnot. And obviously, we're talking Northern Hemisphere. So, why is it that the winter solstice, which is clearly when we are receiving the least amount of solar heating, that's not the coldest? That the coldest comes after that? Has that ever crossed your mind? Well, here's the thing. When it's wintertime, we're receiving less heating, and so the Earth, it's hot. It's receiving less radiation than it's giving off, so it cools. And it will continue to cool until the amount of radiation it receives exceeds how much it's giving off. And so even when we have the least amount of radiation, the Earth is still giving off more than it's receiving for a few months after that, which means it's still going to cool down until the amount that we receive picks up enough to pass the amount that we're giving off. And so there's a lag because it's not in equilibrium. We're not just always in equilibrium with the radiation. And so the same occurs during the summer. We receive the most solar radiation at the end of June. But your hottest days are the end of July and the beginning of August, because you're still receiving more radiation than they're giving off until you get there, hence the temperatures are slowly going up still. So yeah, I said that's one of the homework questions as well. Make sure I cover that with gusto. Okay, now, where the sun rises. In the summer, the sun is, we're pointing toward the summer, which means from our perspective, the sun is north of the equator. In fact, in the summer solstice, how many degrees north of the equator is the sun going to be? How much are we tilted? 23.5 degrees. So if we're tilted 23.5 degrees, and we are tilted toward the sun as much as we can get, how high is it above the equator? 23.5 degrees. So the summer solstice, the sun is at 23.5 degrees north. What about the winter solstice then? 23.5 degrees south. So the sun will be between 23.5 degrees north and 23.5 degrees south, depending on where we are in the season. So that defines two more points on our globe. I should actually go back to a globe here. Two more points on the globe that are 23.5 degrees north and south of the equator. 23.5 degrees north is the farthest north the sun can be. 23.5 degrees south, the farthest south the sun can be. We call the region between those the tropics. So the tropics are the places where at some time during the year the sun can be overhead. If you're not in the tropics, the sun will never be overhead. And you have the Tropic of Cancer, which I believe is the northern tropic, the Tropic of Capricorn, the southern, and it's because of the constellation the sun is in, I think, during a lot, during the solstices. So that's how the tropics are defined because of the tilt. The Arctic and Antarctic circles because of the tilt. What would happen to the seasons on Earth if instead of being tilted 23.5 degrees, we had no tilt at all? If we just went around with our spinning around an axis that's parallel to the axis we're orbiting around the sun.
Would we not have seasons?
We would not have seasons at all. It would be colder at the poles and warmer at the equator constantly. What if we went the other way? What if we were like Uranus and we were going around the sun like this? What would that do to our seasons?
It would be daytime hours on one side and nighttime hours on the
It
other.
would be super extreme. When you're like this, you would have full-on sunlight continuously. You'd bake, right? And so that's what Uranus is like. It's tilted like very close to 90 degrees. I think it's 94 or something. So it's got an 84-year orbit around the sun. And for half of it, its North Pole receives sunlight. So its North Pole receives sunlight for 42 consecutive years. And then it goes into 42 consecutive years of no sunlight, which is crazy, yeah. So you'd have the most extreme weather, seasons, I should say, if we were tilted 9 degrees, and no seasons if we weren't tilted at all. Now to this slide. This slide is showing where the sun rises. So if you are in the middle of, well, if you are somewhere close to the summer solstice, then the sun is 23.5 degrees north of the equator. So in the morning, when the sun rises, when you look off to the horizon and you point east, the sun isn't going to be straight east. Where's it going to be? At summer solstice, where's the sun with respect to the equator?
It's is it in the northern? It's in the northern hemisphere. So it's above the equator.
So it's 23.5 degrees north of the equator. So I'm not pointing the right direction, of course, because I'm actually pointing west right now. East. So when the sun rises in the east, instead of the sun being here, if we are in the middle of the summer solstice, the sun is going to be up there 23.5 degrees north. So I'm going to see the sun rising north of east. But of course, what is our latitude here on Earth? In Lincoln, Nebraska, our latitude. I should be clear, because you can go other places on Earth. It's about 40 degrees north latitude. Even though we're 40 degrees north latitude, we see the sun as 23.5 degrees north of us because it's really far out there. It doesn't matter where we are in the Earth. When you're looking off to the side, it's going to be out there. But when it comes to noon, the sun rises up, and we're 4 degrees, it's 23.5 degrees. That's 16.5 degrees south of us. So at noon, the sun's going to be 16.5 degrees south of straight overhead, south of our zenith. So when it rises, it'll be north. At noon, it'll be south of us. Then when it sets, it'll go back north, if it's the summer solstice. Now what about the winter solstice? Where's the sun with respect to the equator, the celestial equator, winter solstice? 23.5 degrees south. So once again, here, 23.5 degrees south is down there. Then it goes up in the sky, 23.5 degrees south, we're 4 degrees north. That's 63.5 degrees from overhead. Or to put it another way, that's only, 26.5 degrees above the horizon at noon in the wintertime here. So it never gets all that high. You don't even think about that. But during the winter, the sun doesn't get all that high. It's only up about here. During the summer, it's up about here. And so, you have a south-facing window in your house. You very much see a difference in the shadows cast or where the sun shines in, depending on the season. In the winter, the sun will shine way into the house because it's low on the horizon. Does that all make sense? Is it all totally intriguing and interesting? Right, Boring, you silly? I hope not. Now the precession. I think it was Aldwin that brought up that the North Star is not always the North Star. The Earth is like a top spinning, and when you have a spinning top, it doesn't just sit here stationary spinning about an axis. It goes around like this. And that's called precession, and the Earth is doing that. And so the Earth's North Pole over time moves around, and I was right for once. It's 26,000 years for it to do one complete precession cycle. So in 26,000 years, Polaris will be the North Star again. But in between, it'll move very far afield. So here's a picture showing the path on the celestial sphere where the North Celestial Pole moves over a 26,000 year period. And so you can see, of course, right now, the North Celestial Pole is almost exactly where Polaris is, just barely off. But, if we were to go to about 3,800 years ago or something like that, then Turban would have been the closest we would have to a North Star. You come around and you can see North goes here through Cepheus and comes over here in Cygnus, and eventually in 14,000 years, or actually we only have to wait another 12,000 years to get to 14,000, Vega will be the closest thing to a North Star we have. To me, that's really interesting just to think about that it's not constant, because as far as we're concerned, looking at in our lifetimes, we're never going to notice a change. But we can measure very slight changes with very precise telescopes to see that that's what's going on. And of course, we have physics models that you've seen at top, and we analyze those things to death to make the predictions of what should happen, because nobody has experienced these things. Recorded time goes from something like this to this. That's the only recorded time. And in terms of recorded time, I don't think anybody's been saying the pole star was. I could be wrong. This tilt and where we're pointing also affects seasons. I've already talked about these facts, so let's just move on. And this I demonstrated last class period with my walking around the table, that the Earth has to do more than one rotation to go from noon to noon. But now we're going to get to a little more math of it. So if we do a complete cycle, one rotation as measured by the stars, what we call a sidereal day, the time it takes to do exactly one rotation is 23 hours, 56 minutes, and 4.09 seconds. Not 24 hours, that's 3 minutes and 55.51 seconds short of 24 hours. And as we had on the quiz, it's because the Earth is rotating the same way that it's orbiting, and so it has to do more than one rotation to get to the new day. So the sidereal day is the day as measured by the stars. The solar day is the day measured from noon to noon. Now, noon to noon is not consistent, but the mean solar day is taking the average over an entire year of going from noon to noon, and that's what gives you the 24 hours. Because, we just tend to think it's 24 hours in a day and don't realize that's just the average. Each individual day is a little bit different. We use our clocks and cut it up as if it's exactly the same. So, how many mean solar days are in 1 year? We should have two answers this time. Boom, Daniel is in. And there we go. So with two people, we were able to get two different answers. So let's start with, what is the closest whole number to the number of days in the year? 365. 365 is what we usually say until we start thinking, well, no, because we have the leap years. And so how often do we have leap year? Okay, once every 4 years. So if we had leap year once every 4 years, with that leap year, you're adding an extra day. Well, if you do it every 4 years, that means each year you're adding a quarter of a day on average. So that would be 365.25. But that's not correct. The correct answer is this one, 365.2422. So if you go back to the time of Julius Caesar, he had an astronomer, it's in the textbook who it was, he had an astronomer set up a calendar for him to account for the year not being 365 days. And so the Julian calendar added a leap year every 4 years. And most people think that's what our calendar does today. But that's not what it does. The calendar we have today is called the Gregorian calendar. Pope Gregory, I'm sure there's a number that comes after that, had astronomers set this one up to make more sense. To make it more accurate. So here's what the Gregorian calendar has. 365 days per year, except add leap day every 4 years, except drop leap year every year divisible by 100, except add, or leap day, not leap year, a leap day every year. I'm just sorry, you can't read this at all. Divisible by 400. I'm guessing okay, some of you guys do know a lot. So maybe some of you did know that that's what our Gregorian calendar does. Why? Because you have a homework problem that requires you to do this for a different day. So that's what we need to know the why of it so you can do that homework problem. So why is because they're trying to get it closer to the right time. Let me add a page here. So let's do this. We start with 365 days per year. And then we add one leap day every 4 years. So what's the average if it's one leap day every 4 years? Okay, we're adding 0.25, right? That's the fractional part. But then we're subtracting it every 100 years. So if we subtract every 100 year, how much are we removing on average per year? Notice with the adding one every 4 years, we just took 1 divided by 4. So if we're taking one away every 100 years, I had to put a minus sign, and it's going to be 1 divided by 100, which is 0.01. But then we add it back every 400 years, so 1 divided by 400. So we add this all together. If you want to do these partial adding, right here it gave us 365.25. So here it was 365.24. In the end, we have 365.2425 days per year with the Gregorian calendar. Well, we could go further, but they figure there are enough things that affect and change it that there's no point going any further. You know, things like, what was it, 2004 or so, there was the Aceh earthquake, the earthquake that caused all of the tsunamis in Indonesia. And that was like a 10-meter lift in the ocean floor. That's a huge distance, 10 meters. You can think of it as 10 yards, it's roughly the same. And so, when you spin around and you put your hands out, what does that make you do? It slows you down. And so it slowed the Earth down, made the day a little bit longer. And so those kinds of things make it so there's no point in going more precise because the Earth actually varies at some level. So you're going to have to figure out one to come with 365.170, I think it is. And I'll get you started off. What is a fraction that's really close to 0.17? A fraction, so like 1 divided by something. There are other fractions, but it is 1 divided by something that works out here. Well, in your calculator, just try putting 1 divided by 0.170 and take the number that's the closest to that, and you say, okay, so I'm going to add or subtract every this much year, and then you get a new number, and then you work from there. If you have questions, feel free to come and ask me. I can help you through it. But I want you to think about it and really understand the process that went into coming up with this calendar. Okay, I'm out of time.